Hello everyone. What we'd like to do in this section and in the next section is we're going to learn about a set of trigonometric identities or trig formulas that are super useful. Now I have to comment that you don't necessarily need to have these committed to memory. What you need to do is just know that these formulas exist, and when the appropriate time arises, be able to use them. So what we're going to learn in this video is something called the addition and the subtraction formula. Now, in this specific video, I'm not actually going to derive these formulas for you. I will introduce them, I'll show you how to work with them, and then in the next video, we will prove them. Okay, so let's first motivate why we would even want an addition or subtraction formula. Well, for example, when we're evaluating any of the 6 trig functions, if we want to find their exact values, they have to be a special number on the unit circle. For example, we can evaluate any of the 6 trig functions as long as the angle is a multiple of 30 degrees or a multiple of 45 degrees. Or if we're working in radians, we could evaluate any of the 6 trig functions as long as the angle in radians is a multiple of pi over 6 or pi over 4. So, for example, we could figure out what the cosine of 30 degrees is. Cosine of 30 degrees, all right, we could do the hand trick. We could put down our 30-degree finger. Cosine is the x-coordinate. Cosine of 30 degrees is root 3 over 2. Or similarly, we could figure out what the cosine of, let's say, 45 degrees is. These are nice numbers on the unit circle. Put down our 45-degree finger. Cosine is the x-coordinate. Cosine of 45 degrees is root 2 over 2. But what we want to be able to do is, what about if we wanted to know cosine of like 75 degrees or cosine of, let's say, 15 degrees? What if we were to take those nice values on the unit circle and add them and subtract them? What would be the cosine sign, or what would be the values of the 6 trig functions at those locations? So what I mean here, let's kind of write this down, is like what would be the cosine of 75 degrees? Or what would be the cosine of, let's say, 15 degrees? These aren't nice numbers on the unit circle, but it's nice to note. It's nice to note that this could be the same thing as the cosine of, well, this is the same thing as 30 degrees plus 45 degrees. Or over here, this could be the same thing as cosine of, let's say, 45 degrees minus 30 degrees. So if we're thinking about this, we're saying, hey, there would be I wish there was like some nice formula that had to do with the cosine of a sum of angles, or the cosine of the difference of angles. Similarly, we could do this, I could make the same thing if these were sines instead, or even tangents. So we are craving, you know, our math mouths are watering for a formula that tells me, how could I work with something like this? You know, how could I work with something like this? It would be nice if the cosine distributed. It doesn't, unfortunately. But we would like a formula for the cosine of 30 degrees plus 45 degrees. We would like the formula to just have like a cosine of 30 degrees piece in it, and a cosine of maybe 45 degree piece in it. So then we can do those evaluations. So what we have here to solve this type of problem is we have the addition and subtraction formulas. Let me go ahead and write them up on the board, and then we'll see how we can actually evaluate cosine of 75 or cosine of 15 degrees. Okay, so let's write them down. Okay, so there's one for sine. Okay, so how about I put sine of how about we put theta and phi. I think the book uses S's and T's in the section 7.2 chapter, I guess in the material there, and it uses X's and Y's in the back of the book. I'll show you here in just a second. But we want a formula for the sine of theta plus phi. It'd also be nice to have a formula for the sine of theta minus phi, or it'd be nice to have a formula for the cosine of theta plus phi, and for the cosine of theta minus phi. And same thing with tangents. I'll write those down in just a second. Okay, so what are the formula for them? Again, I'm not going to prove them right now. I'm just going to list them. We're going to just learn how to work with them, and then we'll prove them. Okay, so how do I remember these? And how am I, what's a trick that I use to memorize all these kind of funky trig formulas that we're going to teach that I'm going to teach you about in the next 2 sections? I give sine and cosines personalities. These functions, they're I don't know, they're like dogs, you know. Each dog, you know, they have their own, you know, they have their own unique little personality. You know, even though you have two labs, you know, you can tell that they're different. You know, they got their own little quirks. Same with sine and cosine. They have personalities. Sine. Sine is a very shy function. Very shy, very reserved. It likes to share, though. Very friendly, likes to share, but it's also a little bit shy. A little bit shy. It also likes to follow the rules. Cosine. Cosine. Cosine is very selfish. A very selfish function. Cosine freaking loves itself. And cosine doesn't like to follow the rules. Cosine is a rebel. Cosine is a rebel. So sine is a little shy. Sine is shy. Cosine, cosine, so selfish. Freaking loves itself. What a rebel. Okay, let me show you what I mean. Sine, a little shy, but it's also friendly. Shy and friendly, you know? You know, once you get to know sine, you know, it's a little shy, but once you get to know sine, it's friendly. So sine likes to share. Sine of theta, cosine of phi. Okay, it likes to share. They're next to one another. Okay, sine also likes to follow the rules. If there's a plus here, there's a plus here. It doesn't like to oppose the rules. Okay, and then the same thing, just with swapped angles. Sine of phi, cosine of theta. Okay, now the only difference between the addition formula and the subtraction formula is a plus or minus. So again, sine is a little shy, but it's friendly. Shy but friendly. Okay, so it has a sine and a cosine together, and it likes to follow the rules. Okay. Now let's talk about cosine the rebel. Cosine, remember, cosine freaking loves itself. Cosine says, hey, me, cosine theta, cosine phi, me, cosine theta, cosine phi. And then, it doesn't like to follow the rules. It's a rebel. If there's a plus here, it says, no, minus. And then it's kind of throwing sine on the back burner. It wants itself first. Sine of theta, sine of phi. Okay. Same thing. Now the only difference between the addition and the subtraction formula is I guess the sign in the middle. So here, still, cosine loves itself. Get over yourself, cosine. Get over yourself. Okay, it says minus. There's a minus here. Cosine says, I'm a rebel. I'll do a plus. And then it's always throwing sine on the back burner. Okay. So here are the addition and subtraction formulas, and a little cute way to think about their formulas. And again, those personalities I gave sine and cosine don't just apply to these addition and subtraction formulas. You'll see they'll also apply to these double angle formulas we'll talk about, the half angle formulas, which we'll talk about, and there's also these power reducing formulas we'll talk about, and they still display those same type of personalities. Okay, there's also a addition and subtraction formula for tangent. I definitely don't have this one memorized. The tangent of theta plus phi. Okay, like if I was in a pinch, I would just say, you know what, tangent is the same as sine over cosine. You know, I would say, hey, this is sine of theta plus phi over the cosine of theta plus phi. And since I have these ones memorized, I could figure out what the addition formula for tangent would be. And that's exactly what I'm going to do and actually prove this formula to you in the next video. But it does have a formula that's not in terms of sines and cosines, but it's just in terms of tangents. Okay, so notice I'm going to look at my notes because I don't have this one memorized. Okay, for this one, it's the tangent of the first plus the tangent of the second all over. I think it's going to be 1 minus the tan of theta, tan of phi. And there's also the tan of theta minus phi. The only difference is that the signs change. So this will be the tangent the tangent of theta minus the tangent of phi, all over 1 plus the tangent of theta tangent of phi. Okay. So, in the case that you do not have these memorized, well, the back of the book is going to be your best friend. So let me show you. All the trig identities that we're going to learn in this section and in the next are all in the back of your book. So the very back of your book, you'll see them all here. Let's see, where are we doing? We're doing the addition and subtraction formulas. There they are, addition and subtraction formulas. They're using x's and y's. I was using thetas and phis, but there they are. And we'll soon learn about these double angle formulas. There's these power reducing formulas. I think that's that would be the top right. And then formula for reducing powers. And I'm trying to read and hold this up at the same time. And then there's half angle formulas, which we'll also learn about. Okay. All right, so here are the formulas. Let's just get practice with using them. All right. Again, I highly, highly, highly recommend that you watch my video for the proof of these formulas. It's very accessible. And all the other formulas that were derived are direct consequences of these addition and subtraction formulas. So if you put in that hard work to understand the proof of where these formulas come from, you'll easily be able to understand where the other formulas come from. Okay, so let's see. We had on the board a second ago. Can we figure out what the cosine of? Let's do the 75 degrees. Okay, well, this is the same thing as the cosine of, well, what do we know on the unit circle? So 45 degrees plus 30 degrees. So there is a formula for this, okay? So remember, cosine frickin' loves itself. Cosine of 45 degrees, cosine of 30 degrees. Come on, cosine, get over yourself. Okay, always disobeying the rules. Sine of 45 degrees, sine of 30 degrees. Throwing sine on the back burner. Okay, now we know all these values. Cosine of 45 degrees. Put down our 45 degree finger. That'll be root 2 over 2. Okay, cosine of 30 degrees. We'll put down our 30 degree finger. That's root 3 over 2. Minus sine of 45 degrees, put down a 45 degree finger, that's the y coordinate, so that'll be root 2 over 2. Okay, sine of 30 degrees, put down our 30 degree finger, that'll be root 1 over 2, or 1/2. And there we have it. Alright, so let's multiply this together. Okay, so when I multiply root 2 times root 3, I guess just remember that I guess something that's nice to know is the square root of a times b is equal to the square root of a times the square root of b. Be careful that this is actually only true if a and b are both positive. So we are going to use this rule in this direction. Okay. So we have the square root of 2 times the square root of 3 is equivalent to the square root of 2 times 3, or the square root of 6 over 2 times 2 is 4. Minus, this will be the square root of 2, all over 2 times 2, which is 4. We have a common denominator of 4, so this will be the square root of 6 minus the square root of 2, all over 4, and this is the exact value. This is the exact value of the cosine of 75 degrees. Okay, what's a great way to check our work? Use our calculator. Okay. When you're doing these exercises, if you're using your calculator just to get the answer, you're cheating. The whole point of these type of exercises is to try to figure out the exact value of these without your calculator. However, at the end, use your calculator to check your work. Okay, so let's make sure that cosine of 75 degrees is equivalent to the square root of 6 minus the square root of 2, all divided by 4. Okay, first of all, let's make sure our calculator's in degree mode. Okay, I'm in radian mode, so I better switch to degree mode. Okay, let's see the cosine of 75. Okay, I'm getting roughly 0.259. And let's also do the square root of 6 minus the square root of 2, all divided by 4. Would you look at that? So, the same. How beautiful. Fun. We did it. We did it. We did it without a calculator. You know, we just used it to check our answer. But how fun. How fun. Okay? Cool. Okay, so I recommend, try to figure out what the cosine of 15 degrees would be. We're going to do just some more examples. Okay, let's do some more. Okay, let's say that we want to know what what's the sine? Let's say we want to figure out what the sine of 13 pi over 12 is. Okay, we're trying to figure out the exact value of this, again, without using our calculator. Maybe go ahead and pause the video and see if you can think about this one on yourself before we do it together. Okay, let's do it. So what we want to be able to do here is notice that 13 pi over 12, this isn't a multiple of pi over 6, and it's not a multiple of pi over 4. It's not a nice number on the unit circle. So what are we going to do? I'm going to try to break up 13 pi over 12 into either the sum or the difference of numbers we do know on the unit circle. Now, there's not necessarily a unique way to do this. So maybe I'll show you we can do this in two different ways. So if you don't like working in radians, of course you could convert this to degrees if you'd like, but let's work in radians. Okay, so I need to break up 13. Into two pieces, so when I divide it by 12, I'm going to get multiples of 6 and multiples of 4. So let's see here. We could break 13 up. How about 13 pi over 12? This could be the same thing as, how about 9 pi? We could do 9 pi plus 4 pi, I think that would work, over 12. Okay. I think you could break this up as 10 pi and plus 3 pi, I think would work also. Let's stick with this one. It's the first one I've written down. So this will be 9 pi over 12 plus 4 pi over 12. Okay, what does this reduce to? So what is this? This is going to be 3 pi over 4. Plus, what will this be? This will be pi over 3, or this is 2 pi over 6, so it still is kind of a multiple of pi over 6. Okay, so this will be the same thing as sine of 3 pi over 4, plus pi over 3. Let's erase this. So let's use the addition formula for sine. Okay, sine is friendly. Yeah, sine of 3 pi over 4. Yeah, cosine, you can come along. Cosine, even though cosine you're kind of an a-hole, sine's still friendly. Sine will still invite you to the party. Okay, sine likes to follow the rules. So then sine of pi over 3 cosine of 3 pi over 4. Okay, so let's think where we are on the unit circle. Okay, so we're at pi over 3. So here's pi over 3 is two increments of pi over 6. So 1, 2. That's 2 pi over 6. Okay, so sine and cosine here. Here's pi over 3. Guess we could just put down our pi over 3 finger. What's that? Root 1 over 2, or 1/2 and root 3 over 2. Okay, 3 pi over 4, we need to move 3 increments of pi over 4, so 1, 2, 3. Or you could think that 4 pi over 4 is at pi, and you could take away 1 to get to 3 pi over 4, either way. So this will be what? 3 pi over 4. Okay, so let's think about what sine and cosine of 3 pi over 4 would be. Well, if I'm thinking about what the reference angle, that would be what? The reference angle would be pi over 4. So think about what this would be in the first quadrant. Be root 2 over 2 and root 2 over 2. So cosine, root 2 over 2, sine, root 2 over 2. Okay, now we just got to adjust the sign. Okay, well, cosine is negative and sine is positive in quadrant 2. So I think we have all the information that we need here. Okay, sine of 3 pi over 4 will be root 2 over 2. Okay, cosine of pi over 3 will be 1/2. Okay, plus sine of pi over 3, that'll be root 3 over 2. And cosine of 3 pi over 4 will be negative root 2 over 2. Okay. Sweet. All right. So let's just evaluate this, or just clean this fraction up. So what is this? This is the same thing as root 2. This is root 2 over 4 minus, since I have a subtraction sign there, root 3 times root 2 is the same thing as root 6 over 4. Or how about we get root 2 minus root 6 all over 4. So this should be the exact value of sine of 13 pi over 12. Okay, let's use our calculator to check our answer. Okay, so I need to make sure we're now in radian mode. So mode, switch out of degrees, back into radians. Okay, so let's do sine of 13 pi divided by 12. Okay, I'm getting like negative 0.259. Okay, and let's also do the square root of 2 minus the square root of 6, all divided by 4. They're the same. How sweet. How sweet. Okay, so what I'd like to just show you now is that it wasn't necessarily, we didn't have to break up 13 pi over 12 as 3 pi over 4 plus pi over 3. We could have broken this up differently. Okay, so I think we could say that 13 pi over 12, well, I think we could use even 10 pi plus 3 pi. I think this would be a fine way to break it up. So this would be the same thing as 10 pi over 12 plus 3 pi over 12. Okay, so let's see, what are we going to get here? This is the same thing as, let's see, this would be what, 5 pi over 6 plus, what else? This will be pi over 4. So we could work with this. So this will be what, 5 pi over 6 plus pi over 4. Pi over 4. So this is sine of 5 pi over 6 times the cosine of pi over 4 plus, cosine likes to follow the rules, sine of pi over 4, and then cosine of 5 pi over 6. Okay, let's think about this on the unit circle. Okay, where are we at? Okay, well at pi over 4, that's right here. Okay, again, that's root 2 over 2 and root 2 over 2. Okay, 5 pi over 6, where are we at? Where you could count 5 increments of pi over 6. 1, 2, 3, 4, 5. Or you could think at being at 6 pi over 6 or being at pi and taking away 1. So here, so this is pi over 4. This is 5 pi over 6. Okay, the reference angle here would be pi over 3. So what's sine and cosine of, pi over 6 would be the reference angle. So what are sine and cosine of pi over 6? Well, that would be what? Root 3 over 2 for the x-coordinate, and root 1 over 2, or 1/2 for the y-coordinate, and cosine is negative in that quadrant. Okay, so let's see what we get here. Sine of 5 pi over 6, that's 1/2. Okay, cosine of pi over 4 is root 2 over 2. Okay, plus, okay, sine of pi over 4 is root 2 over 2. And cosine of 5 pi over 6, that's negative root 3 over 2. Okay, so what do we get here? This is the same thing as what? Root 2 over 4 minus root 6, and it'll all be over 4. The same answer. Isn't that sweet? Isn't that sweet? Okay, so it works this way too. Fun. All right, let's do another one. I'm going to go ahead and erase what I have here. Okay, let's say that we wanted to calculate, I don't know, how about we do cosine of 165 degrees. Go ahead and pause the video and give a shot at doing this one here. Okay, let's do it. Well, let's think about how we can make 165. So let's see. Well, 45's got to be in there. If it's going to be on the unit circle, I mean, I need a 45 degree in there. And if I take away 45 degrees from that, what will that be? 100 and what? 120 degrees. So I think that these are both on the unit circle. So this could be the same thing as cosine of 120 degrees plus 45 degrees. So this will work. Okay, so this will be the same thing as cosine of 120 degrees. Remember, cosine frickin' loves itself. Come on, cosine. Come on, where's the love, cosine? Minus sine of 120 degrees times the sine of 45 degrees. Okay, well, let's think about where we're at. Okay, hopefully we're pretty comfortable with 45 degrees. Okay, well, 120 degrees. Well, I think that's a multiple of 30 degrees. So I think that's 4. So move 4 increments of 30 degrees around the unit circle. Okay, so we're at, I guess, at 45 degrees. For completeness, I guess maybe we'll write it. Okay, that's root 2 over 2, root 2 over 2. Okay, 120 degrees, I need to do 4 increments of 30 degrees. So at 1, 2, 3, 4. So right here. You could think of this as like 90 degrees plus an extra 30 degrees if you like. Okay, so let's see, what would be sine and cosine here? So it's 120 degrees. Okay, well, the reference angle would be what? Pi would be what, 60 degrees. So what's sine and cosine of 60 degrees? Well, that'll be 1/2 and root 3 over 2. But again, we're in the second quadrant, so cosine is negative here. So a negative 1/2. Okay. So let's see what we get. Cosine of 120 degrees is a negative 1/2. Cosine of 45 degrees is root 2 over 2. Minus sine of 120 degrees is what? Root 3 over 2. And sine of 45 degrees is root 2 over 2. Sweet. Okay. So what are we going to get here? This is going to be negative root 2 over 4 minus a root 6 over 4. So I guess we could say this is equivalent to, let's just write it here, to how about negative root 2 minus root 6 all over 4. Another way to commonly write this is to factor the negative completely out and move it in front of the fraction bar. So you could write this as root 2 plus root 6 all over a4. These are all equivalent. Okay, let's check our answer. Let's check our answer. So mode, let's make sure we're in degree mode now. Okay, so what is the cosine of 165? Okay, and then we need to know what is negative. The square root of 2 plus the square root of 6, all divided by 4. Check it out. I put the negative all the way out front, and they're the same. Awesome. Cool. Okay. For fun, maybe this would be a good exercise for you to try on your own, but it should work the same. You know, what if we tried to get a subtraction in there? What if we tried to get a subtraction in there? Let's see. I think we could do 210 degrees minus 45 degrees. That should give us 165. So, you know, maybe this is a good exercise for you to do on your own. But show using the subtraction formula for cosine that we should get the same exact answer we just did. Okay, let's try this next example. See if you can use the addition and subtraction formula for tangent to try to evaluate the tangent of 7 pi over 12. Give it a shot. Okay, let's do it. Okay, so first thing we want to do is break up 7 pi over 12 into numbers we know on the unit circle. So 7 pi over 12. Well, I think we could do 3 pi plus 4 pi all over 12. So this is the same thing as 3 pi over 12 plus 4 pi over 12, or this is what, pi over 4 plus pi over 3. So we want to compute the tangent of pi over 4 plus pi over 3. All right. Okay, so if I have to be honest, okay, if I was on a desert island and I really needed to know the addition formula, or I needed to know what the tangent of 7 pi over 12 was, and I didn't remember the addition formula for tangent, I would do the same thing as sine of pi over 4 plus pi over 3 over cosine of pi over 4 plus pi over 3, and I would use the addition and subtraction, or the addition formulas for sine and cosine. But let's go ahead and use the formula for tangent. Okay, so the addition formula, it'll be the tangent of pi over 4, okay, plus the tangent of pi over 3. This is a perfect time to look in the back at the book if you don't remember what the addition formula for tangent is. And it'll be a 1 minus the tangent of pi over 4 times the tangent of pi over 3. Okay, so we need to figure out what tangent of pi over 4 and pi over 3 is. And we'll draw a quick unit circle. Okay, it's great to know tangent in the first quadrant. Okay, so I hope the easiest one is knowing that tangent of pi over 4 is 1. Well, that's the location where sine and cosine are the same, and tangent is the same as sine over cosine. I also remember that tangent represents the slope of this line that's on the unit circle. The slope here is 1, so tangent of pi over 4 is 1. Okay, there's also tangent of pi over 6, tangent of pi over 6, and tangent of pi over 3. Okay, now you could compute sine of pi over 6 over cosine of pi over 6, or sine of pi over 3 over cosine of pi over 3. It's great just to know these values. What I remember for tangent is these ones are either root 3 or root 3 over 3. And I just ask myself the question, which one's bigger? Well, I hope you believe that the square root of 3 is bigger than the square root of 3 divided by 3. So, and I notice that this slope here is bigger. So tangent of pi over 3, I'm sorry, tangent of pi over 3 is equivalent to root 3, and tangent of pi over 6 is root 3 divided by 3. Okay, so let's go ahead and use that to evaluate this. I'm going to erase this picture right here. Okay. So, tangent of pi over 4 is 1. Okay. Tangent of pi over 3 is root 3 all over. We have a 1 minus. Tangent of pi over 4 is 1. Tangent of pi over 3 is root 3. So, this is the same thing as 1 plus root 3 all over 1 minus root 3. And this is the answer. We have tangent of 7 pi over 12 is equal to 1 plus root 3 divided by 1 minus root 3. Let's use our calculator to check. Make sure we're in radian mode. Okay, we're in radian mode, so tangent of 7 pi divided by 12. And let's also do 1 plus the square root of 3 plus divided by 1 minus the square root of 3. And notice we're getting the same thing. Awesome. So this is the answer. Now, just a comment on this answer. You find that oftentimes, if you're looking at your answers in the back of the textbook, you may think that your answer is wrong, but it's most likely right. Oftentimes the book does not like to have square roots in denominators. So if you're trying to figure out why your answers are different, you could use a calculator to figure out that your answers are the same, but that's not as fun as trying to massage this to look like the book's answer. You may need to rationalize the denominator. So we need to multiply top and bottom by 1 plus root 3. So a nice trick. Okay. So let's just multiply this by 1. Okay, so what would we get out? This will be the same thing as, well, I'm going to get a 1 times a 1, So 1 plus, I'm going to get a 1 times root 3 and another 1 times root 3, so I have 2 root 3's. Or root 3 plus root 3, so I have 2 root 3's. And then we're going to get plus a root 3 times root 3, we'll get another 3. Okay. And when we expand out the bottom, this is like a difference of squares type thing. So we're going to get a 1 times a 1. We'll get a 1 squared, or 1. We'll get a positive root 3, and then we'll also get a negative root 3. The O and the I in FOIL cancel out. And so then we'll get a negative root 3 times root 3. We'll get a negative 3. So this is the same thing as what? 4 plus 2 root 3. 1 minus 3 is negative 2. Okay, so this is the same thing as we could distribute that negative 2. So what do we get? A 4 over negative 2 plus a 2 root 3 all over negative 2. So this will be what? A negative 2. What? How about minus a root 3? So 1 plus root 3 all over 1 minus root 3 is equivalent to negative 2 minus root 3. This is what the book might report. So again, we could use our calculator to verify this. Negative 2 minus the square root of 3. Hit enter. The same thing. How fun. Okay, cool. All right, so now what we're going to do is, let's do some exercises. I guess we're going to do a little bit more, kind of more abstract type exercises. But these are great exercises for understanding formulas and understanding inverse trig functions, understanding how to draw triangles or when to draw triangles. So let's go ahead and do some fun exercises. All right. So let's try to find the exact value. Let's try to find the exact value of cosine of sine inverse of 2/3, okay, plus the tan inverse of 1/2. We want to find the exact value. We don't want to use our calculators. Calculators are not invited to this party, not until you finish the problem to check your work. We want to compute this without a calculator. Go ahead and pause the video and see if you can think about this one on your own before we do it together. Okay, let's do it. The key thing to realize here or to think about is I have these inverse trig functions going on. What do inverse trig functions do? Inverse trig functions eat ratios and spit out angles. So, what is this? This sine inverse of 2/3, this is some sort of angle theta, we'll call it. And similarly over here, this tan inverse, okay, tan inverse of 1/2, that's another angle, we'll call it phi. So really what we're doing here is we are computing the cosine of theta plus phi. So if we're using the addition formula, this would be cosine of theta, cosine of phi, and then cosine doesn't like to follow the rules. Sine, poor sine. Cosine's always putting on the back burner. Sine of theta, sine of phi. Okay, so we need to figure out what cosine of theta is and what sine of theta is. We also need to figure out what cosine of phi is and what sine of phi is. We're going to get all that information by knowing that theta is equal to the sine inverse of 2/3, and also that phi is equal to the tan inverse of 1/2, or we should have that sine of theta is equal to 2/3, and that the tangent of phi is equal to 1/2. Here's a good question. What quadrant is theta and phi have to be in? Both theta and phi have to be in quadrant 1. Why? Okay, well, notice specifically how tan inverse and sine inverse work. Tan inverse and sine inverse only spit out angles between negative pi over 2 and pi over 2. Okay? So I know that sine of this angle has to be positive, so that means that whatever this angle is between negative pi over 2 and pi over 2, well, between 0 and pi over 2, that's when sine spits out something positive. So theta must be in quadrant 1. Similar argument, phi must also be in quadrant 1. Okay, so let's draw a triangle. Let's draw a triangle for these. Okay, I guess if this was negative, then we would know that theta would actually be in quadrant 4 instead. Similarly, if this was negative 1/2, phi would be in quadrant 4. Okay, so let's see. So here is theta. Sine is opposite over hypotenuse. Over here, we have phi. Okay, tangent is opposite over adjacent. Okay, so over here, what we need to figure out, I guess, the adjacent side. So how about we call this x for right now? So if we use the Pythagorean theorem, I think this is going to be the same thing as the square root of 3 squared, so 9, or how about the square root of 3 squared? So I'll write that 3 squared minus 2 squared. So what is this? This is 9 minus 4. 9 minus 4 is 5, so this is the square root of 5. Okay. And over here, the hypotenuse, this is going to be the square root of 4 plus 1. This will be the square root of, how about 2 squared plus 1 squared. This will be the same thing as the square root of 5 here for the hypotenuse. Again, if we were, taking the square root, and if we had to choose a plus or minus here, the reason I'm choosing the plus is because theta, and over here I'm choosing plus also, is because theta and phi are both in quadrant 1. Okay, so I think from this information, basically just from these triangles, we can finish the problem. Okay, let's go ahead and erase what we have here. Just leave the triangles up. Okay, this was root 5. And this here is root 5. Okay, so what's cosine of theta? Cosine of theta is 2. Cosine of theta will be is adjacent over hypotenuse, root 5 over 3. Okay, what's cosine of phi? Cosine of phi will be 2 divided by root 5. Okay, minus. What's sine of theta? Sine of theta will be 2/3. And sine of phi will be 1 over root 5. Okay. So let's clean this up. So I guess what you could do is you could cancel these root 5s right here, but I'm noticing I have this great common denominator already. So this is the same thing as 2 root 5 minus 2 all over 3 root 5. I'm totally fine with this being your answer. But oftentimes the book likes you to not have square roots in the denominator, so let's multiply top and bottom by the square root of 5. Some parentheses here. Okay, this root 5 will distribute in. Okay, what are we going to get? Well, we're going to get 2 times root 5 squared. Root 5 squared is 5, so 2 times 5, that'll give us 10. So we'll get a 10 minus 2 root 5 all over. We get 3 times root 5 squared, so 3 times 5 is 15. So this here is the answer. Again, I would be fine, on an exam, I would be fine with you writing your answer like this. But your book will most likely write this. So that is the answer to this problem here. Really, it just came down to realizing that, hey, these are just angles. These are just angles. All we needed to do is, use the addition formula for cosine, draw some triangles, and then evaluate the sine and cosine of those angles. All right, let's do another exercise. Let's say, for example, that we get a little bit more abstract. So let's say that we have that sine of sine inverse of x plus the cosine inverse of y. Okay. What we want to do here is we want to express this without any trig functions at all. So express without trig functions. So I want to write this with only x's and y's in it. Okay, maybe go ahead and pause the video and think about this on your own before we do it together. Okay, similar to the last example, what do inverse trig functions do? They spit out angles. This is some sort of angle theta. This is some sort of angle phi. So we need to figure out what is the sine of theta plus phi. Okay, well this is the same thing as sine of theta times the cosine. Let's write this down a little bit lower, give ourselves some room. Okay, this is the same thing as sine of theta plus phi. Okay, this is the same thing as sine of theta times the cosine of phi. Okay, sine likes to follow the rules. Plus, we'll have the sine of phi times the cosine of theta. Okay. So what we need to do is we need to figure out what sine of theta is, what cosine of theta is, what's cosine of phi, and what's sine of phi. What are we going to do? We're going to draw some triangles. Well, what we have right here is that theta is equal to the sine inverse of x, and we also have that phi. That phi is the same thing as cosine inverse of y. Or we have that sine of theta. Sine of theta is equal to x, and over here we'll have that cosine of phi will be equal to y. Okay, let's go ahead and draw a triangle. Okay, so here, again, theta is between negative pi over 2 and pi over 2. Here, phi. Well, phi in this case, well, it's cosine inverse, so phi would be between 0 and pi. Okay, so it's nice to keep that in mind. However, when I draw this triangle, I'm just going to think about it in quadrant 1. I'll show you why in a second. So let's think about this as theta. Okay, so this is the same thing as x over 1. So this will be an x and this will be a 1. So sine is opposite over hypotenuse. Over here, okay, this will be phi. Think of this as y over 1. Well, cosine is adjacent over hypotenuse. Okay, so let's figure out the missing side. Okay, over here, if we want to do the missing side, using the Pythagorean theorem, I think we're going to get a square root of 1 squared minus x squared, 1 squared minus x squared, or just square root of 1 minus x squared. Okay, well, I guess if you were using the Pythagorean theorem, when you take the square root, you would think about a plus or minus here. Why am I choosing the plus? Well, theta is always between, for sine inverse, it's between negative pi over 2 and pi over 2. Well, if we're in either, I guess, quadrant 4 or quadrant 1, well, this length right here, the one we were looking for, this will always be positive in one of those quadrants. Always the x-coordinate, I know there's an x here, but the width here is always positive, in quadrant 4 and quadrant 1. So that's why I'm choosing the positive here. Similarly over here, this will be the square root of 1 minus y squared. Okay, this is a height here. Why did I not do a plus or minus here? Why just the plus? Well, let's think about it. Well, cosine inverse, this is cosine inverse. Cosine inverse spits out angles between 0 and pi. I'm looking for the height here, and the height on the unit circle is always positive between 0 and pi. So that's why I'm always having a positive here. That's why I'm picking the positive square root. Okay? So I think from these triangles that we can figure out everything. Okay, let's erase what we have here. We'll just leave the triangles up. Okay? So, sine of theta. Okay, theta, well, sine is opposite over hypotenuse, so this will be x over 1, or just x. Cosine of phi, well, cosine is adjacent over hypotenuse, so this will be a y over 1, plus sine of phi. Well, sine of phi is opposite over hypotenuse, so this will be the square root of 1 minus y squared all over 1. And cosine of theta is adjacent over hypotenuse, so this will be the same thing as the square root of 1 minus x squared all over 1. Let's go ahead and erase this. So, we have that. And I want to rewrite this expression. But I rewrote this sine, kind of composed with the sum of these inverse trig functions, is really just the same thing as x times y plus the square root of 1 minus y squared times the square root of 1 minus x squared. How cool is that? All just comes down to just drawing some triangles. Beautiful. So here's the answer. Okay, let's do another exercise. Okay. Let's say that we want to know. Let's say we want to know what the cosine of theta minus phi is. Okay, but we know a little bit of information about theta and phi. Okay, in this case, they are telling us that the tangent, let's say that the tangent of theta is 4/3. Now, notice here that it doesn't saying a tan inverse here, so I need a little bit more information. There are multiple angles that spit out a tan. There's multiple angles that give you a tan of that angle equaling to 4/3. So we need information about the angle. In this case here, let's say that theta is in Q3. Theta is in quadrant 3. Okay? Let's say they also tell us that sine of phi is equal to, how about the negative square root of 7/4? And how about we know that phi is in quadrant, let's say 4. Okay. What we want to do is we want to find the exact value of cosine of theta minus phi. Go ahead and pause the video and see if you can figure this out on your own. Okay, let's do it. Well, let's use the subtraction formula for cosine. So here we have cosine of theta minus phi. Well, that'll be equal to the cosine of theta times the cosine of phi. It'll be plus the sine of theta and the sine of phi. Okay, so we need to know what sine and cosine are of theta and what cosine and sine of phi are. So what are we going to do? We're going to draw a triangle. Okay, so let's start here. We have that tangent of theta is equal to 4/3. Tangent of theta is equal to 4/3. Okay, here is one of the most common mistakes that I see students make. They say, oh, well, isn't tangent the same as sine over cosine? And you would say, well, does this not imply that tangent of theta is equal to 4 and that sine of theta is equal to 4 and that cosine of theta is equal to 3? Maybe pause here for a second and think about why this makes no sense. Well, what do sine and cosine spit out? What is the range of sine and cosine? If you think about the graphs of sine and cosine, their amplitude is 1. Sine and cosine only spit out things between -1 and 1. There is no angle that you could plug into sine and have you spit out 4. There's no angle you could plug into cosine that would have spit you out 3. This makes no sense. You gotta be careful here. Okay, so we need to draw a triangle. So let's draw it. Okay, what am I gonna do here? When I'm drawing these triangles, I'm going to always imagine that the angle is actually in quadrant 1, and then I'm going to adjust the signs afterward. I just need to mentally note that theta is in quadrant 3, but when I'm drawing my triangles, I will pretend that they're in quadrant 1 and just adjust the sign after. Okay, so this will be, let's see, what is tangent? Tangent is opposite over adjacent. Okay, we need to figure out the hypotenuse. Okay, you could use the Pythagorean theorem here. I hope you believe that this is a 3, 4, 5 triangle. The hypotenuse here will be 5. Okay, and we also have that, we know that sine of phi is equal to negative square root of 7 all over 4. Okay, what am I going to do? Okay, so here's phi. I know phi is in quadrant 4, but I'm just going to kind of ignore this negative for now and adjust the signs at the end. So, let's see, sine is opposite, so this will be root 7 over 4. Okay, let's figure out what this length here is going to be. Well, let's see. Let's call this x for right now. So that's going to be what? The square root of 4 squared minus the square root of 7 squared. So what is this? Is the square root of 16. 16 minus 7. 16 minus 7, what is that? 9. So that'll be the square root of 9. So that'll be 3. So this length here will be 3. Okay, and hopefully, you know, Pythagorean theorem, what is 3 squared? So 9 plus 3 squared plus root 7 squared. So 3 plus 7, what is that? 16, which is equal to 4 squared. So Pythagorean theorem here works. Beautiful. All right. So what do we have here? Okay, I need to be careful with, you know, just looking at these triangles. I need to make sure I know what quadrant we're in. So here, sine of theta will be 4/5. Okay, but we are in quadrant 3. In quadrant 3, sine is negative. And cosine of theta will be what? 3/5. But cosine is also negative in quadrant 3. So we have sine of theta is negative 4/5. Cosine of theta is negative 3/5. If you divide these, you're going to get back out 4/3. Over here, we'll have that what? We already know what sine of phi is. So I guess I'll just write it here. We know that sine of phi is equal to the negative square root of 7 all over 4. And cosine of phi, well, cosine will be what? 3/4? Okay, well, phi is in quadrant 4, and cosine is positive in quadrant 4, so I'll leave this as a positive. All right, we have all the information. We have all the information we need. Okay, so cosine of theta is negative 3/5. Okay, cosine of phi is 3/4. Sine of theta is negative 4/5. And sine of phi is the negative square root of 7 over 4. Okay. So let's just clean this up. So it looks like we're going to get about a negative 9, a negative 9, a negative and a negative. That makes a negative and a negative that makes a positive. So that'll be what? Plus, this will be plus 4 root 7 all over 20. Okay, so I didn't cancel these 4's because I already had a nice common denominator. So here we have it. This is the exact answer of cosine of theta minus phi. It really just came down to drawing a triangle and paying attention to what quadrant we're in. Okay, that's all I have for this video. What we're going to do in the next video is we're going to prove the sum and difference formulas for sine, cosine, and tangent. Again, I highly recommend you watch that video because all the future formulas that we're going to prove in this class, or at least use in this class, are direct consequences from the sum and difference formulas of sine, cosine, and tangent. We'll see you there. Take care.